Just give me 1 second to get this PowerPoint to play nice. All right, sorry about that. All right, we had left off with quiz question number 5. My apologies. I forgot we had to do the quiz question that we started at the end of the last session. And once again, for those of you guys that need PDH hours, you do need to answer 5 of the 8 questions correctly between the 2 dates in order to get the PDH certificate. I'm going to launch this quiz question now. Question number 5. All right. So, an air duct having a surface temperature of 60 degrees passes through a space of 90 degrees and 75 wet bulb. Will the duct sweat, yes or no? All right, we'll give it another 10 seconds here. Hopefully everybody's answered. You should have already been able to do the math at home. And I'm going to go ahead and close the poll now. So click on something. All right, fantastic. It looks like 89% of you had the correct answer, which is yes, the duct is going to sweat. I told you guys before, I'm going to send you guys the workbook for this class, and that is actually one of the questions in the workbook. So I'm going to be lazy. I'm going to pull that up to show you how the answer actually works. Maybe if you can see that. There we go. Now you should be able to see it. So that was, there's a couple work sessions in the workbook. This is work session 1, question 2. And if we look at this on the psychometric chart, I'll blow it up even a little bit bigger for this particular question. So if we take the room air, ceiling cavity, attic, whatever you want to think of it as, it's 90 degrees and 75 wet bulb. So to plot that, we go straight up from 90 degrees on the dry bulb. And a wet bulb, we know we read off the side over here, so we take the 75 line. There's our dot right there. So that's the point at which we're at. It's actually 50% relative humidity in that particular scenario. If we were to introduce that 60 degree cold duct, that is right here. 60 degrees is my duct right here. So anytime that I am below this line right here, right, so here's my dot, 75 degrees, 90 for my attic cavity or whatever it is. If I read straight to the left, that gives me my dew point. So my dew point is 69. So anything that's below 69 on the dew point is going to make dew, i.e. condensation, i.e. sweat. So since 60 degrees is below 69 degrees, we're going to have the duct sweating. All right, let's pull back up our slides and we'll continue on with our course. So we still have 3 more quiz questions left for you guys playing along at home. All right, so picking up where we left off, we had just done the psychometric chart. We built it up. We showed you how to plot points on the chart. We talked about the latent energy versus sensible energy and how to read that enthalpy off the chart and find either one of those two or the total energy. Next thing up on our topic list is mixing air. We kind of hinted at this before on one of the other discussions last Monday. But in this case, I have 2 airflow streams. I have 1,000 CFM of outside air and 3,000 CFM of return air. If I plot those 2 things on the chart for a given example, in this case, my example happens to be 100 degrees outside. Let me get my little laser pointer. It happens to be 100 degrees outside, right here, with a given humidity, in this case, 35%. whatever they happen to tell us. And I have return air in this case of 80 degrees and 50% relative humidity, or 80 degrees and 67 wet bulb. 80-67 is a very common number, 80 dry bulb, 67 wet bulb. That's the temperature at which evaporator coils are rated at. That's the return air that we're assuming you're going to be getting from spaces when we design equipment. In reality, you get totally random things, not totally random, but you get totally different things depending on your application. But 80-67 is what coils are rated at. That's why we have that point here. So in this case, I have a 4,000 CFM total. Outside air is 1,000 of that, so I have 25% outside air, which means if I want to figure out what happens when these two mix, I need to go 25% away from the return air point. Some people make a mistake and they go 25% of the distance from the outside air, but that doesn't make any sense because I have 25% outside, 75% return air. I should be closer to the return air once I mix them. So I go 25% away from the return air on a line between the two. I would plot that dot, and then I would read across, or excuse me, read down. That'd be 85 degree mixed air with, I'm going to make up a number right now, we'll call it 69 wet bulb. That's how you would do mixed air. Figure out which percentage of it is outside versus return air, and then draw a straight line between the two and move that percentage of the way along the line. When we're looking at the CFM of the supply air, we can look at it from both a latent and a sensible standpoint. So airflow is calculated based on the sensible and supply air temperature. The latent is kind of a different discussion, which we'll obviously address as well. But for particular load in the space, we did a load calculation. The total load was 44,000 BTUs of cooling for this particular area of the building. 36 of that was sensible, 8,000 was latent. We would do the CFM based on the sensible, not the 44,000. So if we took our previous formula that we had and we did the math, or did the algebra, I should say, to convert that over to solve for CFM. Remember before we had 1.1 times the CFM times the delta T equaled my BTUs. Well, now I know what the BTUs are. I want to solve for CFM because right on a real project, I'm going to know the load. Before I start the psychometric discussion, I'm going to know the load, and I'm going to be using the psychometrics to figure out the CFM that I need. So I solved that algebraic equation for CFM. So now it's the sensible BTUs divided by 1.1 times the delta T. In this particular project example, it was 58 supply, 75 rooms. So that was my delta T. When I do that math there, it comes out to show me that I need 1,925 CFM. If I want to deliver 36,000 BTUs to that room, I need 1,900 CFM to get it there. Otherwise, I'm not going to get that amount of BTUs to the room. So load calcs come first, then CFM is figured out. And then once you know the CFM, you size the ducts. And once you know all the ducts to all the spaces, you size the main duct. And then once you know the main duct, then you size the air handler. The air handler is the last thing you would size. Unless, of course, it's chilled water, hot water, then you would size the chiller and boiler after you size all the air handlers. Let me open up the question window as well in case you guys are asking questions and I'm not seeing them yet. And so far, let's see. Everyone telling me my sound was good earlier. Okay, no questions at the moment, so we'll keep on trucking. Come back to that later. All right, so let's look at a few different processes here. So one of the processes we want to look at is an adiabatic process. What that basically means is we're going to cool the air by humidifying it. We talked about that a little bit last week. These are called evaporative coolers in many cases. In derogatory terms, they're referred to as a swamp cooler. They are popular in dry climates like Arizona, and they are also sometimes used in like manufacturing and industrial facilities because they are a cheap way to cool without having compression. Now, when I do that in a humid climate, the space is going to be humid and it's going to be uncomfortable in that regard. But if your choices are working in a 110 degree hot manufacturing facility or working in a 90 degree humid facility, you might choose that one just to take the edge off on the heat side. So in this particular example, we have air coming in through an outside air duct. Don't ever build your outside air duct like that. That looks stupid. It looks like a snorkel. But I have a 100-degree day outside and 65 wet bulb, and that correlates to 40 dew point with 36 grains of actual moisture. I run them through this air handler where I'm misting water into the actual airstream itself, directly adding it. This would be direct evaporative cooling. There is also a thing as indirect evaporative cooling. That would be a different discussion. Right now, we're directly adding the moisture into the airstream, so it's direct evaporative cooling. And as we talked about a couple weeks ago, that's actually going to be lowering my dry bulb temperature, 100 down to 70 in this case. But my wet bulb is going to go up. My grains of moisture are going to go up. I'm adding a lot of moisture to the air, so it's going to feel more humid in that particular space, but it'll be cooler. It's a trade-off. So obviously, when I do this, it adds latent cooling load to the space. It removes sensible cooling, but it adds latent cooling. I'm swapping one for the other. As mentioned, it works good in Arizona and other dry climates, sometimes also manufacturing. Sometimes the humidity actually benefits certain manufacturing processes, so it works good in those cases. It can have more increased issues of mold and mildew, so these have to be very well ventilated spaces if you're going to be doing this, or extremely dry, like, once again, Arizona. We look at that process on the psychrometric chart. So same conditions we just talked about on the air handler drawing, 100 degrees, 65 wet bulb, coming out at 70 degrees. So looking at my psych chart, if I plot that out, 100 degrees, boom, 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 and I have 65 wet bulb, 100 degrees, 65 wet bulb right here on the blue line. So I'm at point A right there on that dot. When I add moisture to it, I'm going to go from here up, but I'm going to simultaneously cool it, so it's going to be on an angle because cooling goes from right to left. Moisture addition goes from bottom to top. So I'm actually going to travel along the blue line to point B. I'm going to travel right along this wet bulb line, 65 to 65. The wet bulb did not change. Straight up the wet bulb line. If I want to look at the sensible energy in this particular example, I could just read it from the enthalpy on the chart, or I could do the math. Once again, in this case, energy is 1.1 times the CFM times the delta T. In this case, it was 1,000 CFM, so it's 33,000 BTUs of evaporative cooling. Mathematically, it's a negative 33,000, but verbally, no one would say it that way. I much prefer to do cooling and dehumidification for most applications when I can afford to do that. And that's going to be your normal space cooling like you do in your house or in your office building, restaurant, those kind of things. So I would like to be able to drop both the moisture and drop the temperature simultaneously. That's going to require the use of compression. So in this particular case, I got air coming into my air handler again. It's going to come in at 8067, which is what a normal evaporator coil is designed to handle. So it's coming in at 80 dry bulb, 67 wet bulb. If I look at that on the chart, point A, 80, up the wet bulb line, 67. So I'm at this point right here, 80, 67. I'm going to cool it right to left. I'm going to dehumidify it top to down. So it's actually going to travel on an angle this way. Now in reality, what's going to happen is I am going to start making my evaporator colder and colder, which is going to cool the air down. It's actually going to travel left, hit the 100% saturation line, and that means if I keep trying to make it cooler, it's actually going to pull moisture out of the air, which is going to dehumidify it, which makes me travel down the condensation line like this. So the actual process is going to go right to left, hit the 100% humidity line, and then travel that humidity line down through. And then because I do have bypass air and because I do have waste heat off of my fan, it won't actually end up being on the 100% line. It'll get slightly warmed back up by the bypass air and by the fan waste heat. If I'd like to do the math on this guy here, I can figure out the math with the sensible formula that we just did a minute ago, the latent formula, and then add the two together for total. So once again, sensible, 1.1 times 1,000 CFM times my delta T, 80, dropping down to 55. That's 27,500 BTUs of sensible energy. My latent formula, if you recall, is 0.69, also times the CFM, times the delta grains of moisture, which is vertically up and down on the chart. Right, so that came out to be almost 20,000 BTUs. So when I add the two together, it's 47,000 total BTUs of cooling. All right, let's get quiz question number 6 set up. Number 6. All right. Number 6 is running air across the standard evaporator coil in the cooling mode should have which effect on the Psych chart? Move to the left, move to the right, move down, move left and down, move right and down. So when that process I just showed you, what direction did we move when we had a standard cooling system? Standard cooling system with an evaporator coil. Forgot to reload my coffee before we started, so it's going to get interesting around here. Let's open the question box and see if anybody typed anything in. Andrew asks, for direct evaporative, does the temp of the water spray make a significant difference? It does make a difference. It doesn't make a significant difference. Just like if you were to put a humidifier in your duct system, like at your house or whatever, it makes a difference, but not a significant difference. So in the case of evaporative cooling, it would be more beneficial for me to start with cool water, because then that's less heat that I have to deal with. I don't have the heat of the water. Plus, cool water is what's going to be coming from my city water supply. So there's no reason to heat the water up first to begin with. That would just be an energy waste. But I will have a slightly different benefit if the water is in fact cooler. The examples that we had shown was assuming the water temp was the same as the air temp on the Psych chart. But there would be a benefit to using cooler water if I am doing evaporative cooling. Conversely, if I am adding humidity to a space, that's typically done in projects in the winter, like at a house or like at a library or something like that. So if I have a humidifier adding humidity, usually we would start with warm air when we're trying to add humidity. And we do that because it is, in fact, easier to absorb the moisture into the air. And I, in fact, am in a heating mode in those scenarios. So I'd rather have the warm water to start with. I'm not trying to cool. However, if your humidifier involves electric coils with electrolysis, you may be better off having the cooler water, because the cooler water would have the more minerals in it that would do a better job conducting electricity. Whereas warm water, the minerals are partially, or many of them are precipitated out, so it is harder to then use that with an electric humidifier. So it just kind of depends on what you're doing there. Somebody's asking for a little bit of clarification on the poll question. The poll question is on a standard evaporator coil. So like I would use in a rooftop or residential system, a standard evaporator coil when I'm running in the cooling mode. What is it in fact doing? I'm not sure why it needs clarification. Some people are saying two answers might be possible, but based on you guys voting, that doesn't seem to be the case. So let's go with the process that I just showed on the screen right before the question. I'm going to close the poll in 5 seconds. All right, I'm closing it. All right, so just for clarification, if I go back one slide here, when I'm doing a standard evaporator and I'm cooling the air down, like I had mentioned, I'm cooling it from right to left, and then I'm dehumidifying it downward as well. So it's this blue line here from A to B. So down and to the left is in fact the correct answer. And 80-some% of you guys got that correct. Polls, close poll. Let's answer a few other questions while we're here. Here's a completely loaded question from Paul. How often do rules of thumb regarding CFM per ton roughly equal the math you've shown here? So the CFM per ton is in fact slightly different than what we're doing here. In this case, we have example with 1,000 CFM, and our total tons of cooling is 4,700. So that's 472 CFM per ton. That is on the higher side for mostly what we're doing. Rules of thumb in general are horrible. They're not a good way to do anything at all. They do save time, obviously, but they do lead to lots of problems. If you want to see some of the problems that are caused, join us for the webinar this afternoon at 2 o'clock. We're going to talk about that specifically. In a lot of cases, especially residential nowadays, all the systems that we're putting in that have variable speed furnaces and things like that, we are defaulting the systems to 300 CFM per ton, whereas the historic number has been 400 CFM per ton. The lower the CFM per ton, the more benefits you are going to have on the dehumidification side. Once again, come join us this afternoon's webinar and we'll talk about that a little more. So Henry was asking for clarification on our poll question regarding cooling. He said that he believes that it is D on a high temperature, high humidity day, meaning that it moves left and down. But on a low humidity day, he thinks it's B, it moves to the right. So it can't be to the right because moving to the right means I'm adding heat. So you're saying that when I run my cooling system, I'm going to actually make the temperature warmer. I don't think that is going to ever be a scenario, irregardless of the humidity that it is in the space. Additionally, this particular process is 100% ignoring what's going on with the humidity in the space. Because I'm telling you the entering conditions to the coil in this particular scenario, or any scenario that I'm putting on the psych chart. So the entering conditions in this case are 80 degrees with 67 wet bulb. So 80, 67 is my starting point. That already includes all discussions of humidity in the space. So humidity is completely not part of the discussion in that case. All right, let's go back into the presentation if we can. Make sure you guys have the right screen. You do. Skip the quiz question because we just did it. All right. So we do a load calc for a project. That determines the BTUs that we need for sensible and latent. We use that to figure out the CFM of the air handling system that we are going to be dealing with. By the way, I should have mentioned here, when I said that example there was 472 CFM per ton, that's if I had the sensible and latent together. I'm going to do it based off of the sensible. I'm going to size my air handler CFM off of that. So in that case, it's 275 CFM per ton. So it just depends on what we're looking at too. In any case, so I got my load calc that determines my BTUs. My BTUs determines my CFM. Now that I know the CFM, I got to figure out how big of a cooling coil I need. The cooling coil selection comes before the air handler is selected because the cooling coil selection is going to be based on the amount of surface area that I can get, and the amount of surface area is going to dictate the size of the cabinet of the air handler. So it kind of works in reverse in that regard. There are a few factors here on the cooling coil. The height and length of the coil are going to determine how much surface area you have. Then the amount of rows is going to be a factor as well, right? So if I have 2 rows or I have 4 rows, that'll be a different amount of surface area that I'm going to have available to me. So we'll talk about how that has an impact on this discussion as well. And then the speed of the air is going to come into play. We'll talk about that. And then the fins per inch is going to come into play. If I have 8 fins per inch or I have 14 fins per inch, that's a different amount of surface area that I have going on. So we'll talk about how those things factor into my overall coil selection. In this particular photo, we are showing a refrigerant DX coil, but the same principles would apply if we had a chilled water coil as well. Same idea. It doesn't really care where the cooling source is coming from in this discussion. So if I put this on the psych chart with my cooling coil, I'm going to have examples on here. I have 1, 2, 3 examples on here with different refrigerant temperatures on here. So the red one is a 50 degree, the blue one's a 45 degree refrigerant temp, and the pink is 40. So let's just use the blue one in the middle for our example. So we're going to use the blue line on here. And then the numbers on here, 2, 3, 4, 5, 6, are representative of what's going to happen when I have a 2-row, 3-row, 4-row, 5-row, or 6-row coil. So in my process, A was my room air in this particular example. In this case, it was 75 degrees with, I don't know, 60 degree wet bulb or something like that. D was my outside air. It was a hot 95 degree day. Excuse me, C was my outside air, hot 95 degree day. Those two things mixed to get me my mixed air at D. my mixed air goes to my cooling coil. It starts cooling down, moving right to left, and then it moves on a downward angle to the left as I start cooling and dehumidifying it until I get it all the way down to B, which is going to be the temperature off of the coil. And then that's going to get warmed back up as it mixes in with the space, back to A, and then A and C mix to D, follow the blue line down to B, and we keep repeating. So if I only had a 2-row coil, I'm not going to have a lot of surface area to work with. So my dehumidification is going to be very poor for starters. I'm not going to be able to get down to a low enough temperature to hit the dew point. So I'm going to pretty much move right to left, and that's going to be it. The more rows that I add, let's say I put a 4-row coil in, that's actually a pretty good coil. I'm able to cool right to left, dehumidify on the downward angle, and then a little bit off the line because I got a little bit of bypass air and a little bit of fan reheat discussion. And as I keep getting more rows of coil, it keeps going lower and lower, and I get to lower and lower wet bulbs off the coil. And there's a diminishing return. You can see 0.5 and 0.6 are pretty close to each other when I have 45-degree refrigerant temp. And if I had a 7-row or 8-row coil, it would be like where my red dot's at. There wouldn't be a lot of benefit. So once you get beyond 6 rows of coil, for most applications, that's plenty. There's a diminishing return beyond that because you don't have very much bypass air at that particular point anymore. The bypass factor. So the bypass is how much air is going through the coil that doesn't touch anything. That's the way I like to think of it. So I'm a little air molecule. I'm moving through the evaporator coil. If I'm able to get through all those fins and not touch anything, I'm bypass. The more dense the coil is and the longer the depth is, the harder it is for me to go all the way through without bumping into something cold. So if I have 2 rows or 6 rows, obviously 6 rows means it's a bigger depth. The chance of me getting from point A to point B and not touching one of the fins is low. If I have more fins per inch, that means my gap is smaller. So I got a smaller tunnel to run through as the little air molecule. So I got less chance of making it through. And if the air is moving slowly, I'm going to have more likelihood that I'm going to bounce off of one of the fins versus if it's moving fast, and I might have a chance of shooting right through the gap. So slowing the air down, more fins per inch, and more depth means lower bypass factor. So this is just an example. Looking at that here, this example is showing 80-degree 67, 80 dry bulb 67 wet bulb as my entering condition, which is my standard entering condition for an evaporator once again. And it's kind of showing the best case scenario on this particular coil selection. If I had cooled the air down and then dehumidified it all and there was no bypass whatsoever, I would have been leaving at a 50-degree wet bulb and dry bulb. But because I had some bypass on there, I can figure out how much that bypass was. In this case, it was 6 degrees of bypass. 6 divided by 30, it's 20% bypass. As mentioned, there's different things that affect the amount of bypass. So those same coil rows we had before on the psych chart, 2, 3, 4, 5, 6 rows of coil. Here are typical bypass factors associated with those for DX coils. So as you can see on a 2-row DX coil, 31% of the air typically doesn't touch anything. It goes straight to the coil and touches nothing, right? Right now, for this particular example, we're assuming the same fins per inch for all of these guys. There's more rows associated with it. Whereas if I go to a 4-row coil, 10% gets through. A 6-row coil, 3% gets through untouched, right? So that was the difference here. 2-row, 4-row, 6-row. Significantly better dehumidification when I have less bypass factor, right? You could put 100 rows of coil in there and probably get perfect and nobody bypasses. But 100 rows of coil would be an obscene size air handler with a unrealistic pressure drop to deal with it. The air velocity would also make a difference. So if we were to keep the depth of the coil fixed and then look at various velocities, that would be a factor on here. In this case, 300, 400, 500, 600 feet per minute. The faster I move the air through the coil, the more air actually bypasses the coil. So I want the air to go through more slowly to have a lower bypass factor. In a lot of cases, we are designing air handlers, kind of the rule of thumb there, even though I said don't use rule of thumbs. The maximum criteria for most air handlers is about 500 feet per minute. Otherwise, I start running a greater risk that the velocity of the air will cause enough velocity pressure to blow the moisture that's on the coil off of the coil. I want the moisture to run down the coil and then drip into the condensate pan. But if I use too high of a velocity air, the velocity pressure is higher, it pulls the water molecule off of the coil. It's able to separate it and overcome that frictional resistance, pulls the water droplet off the coil, and then shoots the water droplet into the airstream. That causes two problems. One, I might be introducing humidity into the airstream that I didn't want to do. Remember, my goal is to cool and dehumidify, so why add more moisture back in? The other problem with that is it might be landing on the fan or the fan motor and electronics and things like that and getting those things wet for no reason at all. So keep your air handlers under 500 feet per minute for the coil side of the air handler. On the filter side of the discussion, and we talked about that a couple weeks ago on the IAQ presentation, and if you need a link to the recording on that, let me know. But on filters, we want even slower velocities because then it's easier to filter the air. But for the coil section of the air handler, keep it under 500. And then the slower I do it, the lower bypass factor I'm going to have, and hence the better dehumidification. So sometimes, for dehumidification purposes, we will intentionally slow the airflow down on the air handler to do a better job dehumidifying for that particular moment. So if I have a variable speed drive on my commercial air handler, or I have a variable speed fan on my residential furnace tied to my cooling coil, I can slow those down when I'm in a dehumidification mode specifically and get a better dehumidification rate, which means I'm going to have a lower bypass factor, which means I'm going to have a lower sensible heat ratio as well. The fins per inch are also a factor. So if I keep the velocity fixed and the number of rows fixed in the discussion, and we just talk about changing the fins per inch, here are some examples with that. A lower end, if you will, coil might have 8 fins per inch, which is a 31% bypass factor. And then on the higher end, 14 fins per inch, which granted is going to have a higher pressure drop and cause more fan energy to be needed, but it's only going to bypass 3. So if you want to do a better job dehumidifying, slow the air down, make the coil deeper with more rows, and go to a higher fins per inch on there. When we're doing commercial air handler selection, we have a lot of choices in that regard, and we can pick the coil we want. Residentially, we don't really get to look at this stuff directly. However, residentially, there is the opportunity to pick, quote unquote, a better coil for dehumidification. You don't pick the fins per inch and you don't pick the depth of the coil, but we do have what we call super coils residentially, which just means it's a bigger coil. So it's getting you more surface area that way. Or in some cases, we might put in a slightly bigger evaporator coil as relative to the size of the condensing unit. So those are things we can do residentially, but commercially we get a lot of flexibility. And the amount of flexibility we get depends on what kind of commercial unit we're dealing with. If we have a packaged rooftop unit, especially smaller tonnage ones, we don't have a lot of flexibility. We're basically in the same boat as residential. You got a couple choices, not a lot to work with there. But when you go into the air handlers, the semi-custom and certainly the custom air handlers, then you can pick the coil exactly that you want. On rooftop units, there are other ways to also dehumidify, even if you don't have a lot of flexibility on the coil selection. We do a thing called humidizer. We did a webinar on rooftops last week, and we did include a discussion on humidizer work, so you may want to take a look at that. And for those that don't know, TECmungo, MUNGO.com, click on training, and then click on recorded webinars, and you can see all the webinars we've done in the past few weeks, as well as all the webinars we've done in the past 10 years. They're all recorded on there, and you can check them out. For typical small tonnage packaged rooftop units, we don't have a lot of flexibility. We're going to be given a coil that goes along with the unit. It's already predetermined before you even choose it. It's going to be pretty limited to maybe 4 rows, and it's going to have a reasonably high bypass factor. When you get down to the air handlers, you can start picking ones that have 4, 6, 8, even 10 rows deep, which is kind of crazy, but that will give you lower and lower bypass factors. So you could choose that. In this particular example, 1, 2, 3, 4, looks like a 6-row chilled water coil is what we have. So that bypass factor does change our sensible heat ratio, or the way it's worded on my particular chart, sensible heat factor. If you recall from last week, that is going to be the slope of the line. So depending on which coil I was able to select, or when I change the CFM, or when I change the velocity, or when I change the fins per inch, those kind of things, it changes that slope, which is going to give me a different resulting answer. So the blue line is a 0.75 sensible heat ratio. And I'm putting my ruler on there to line it up with, to make it follow one of these lines over here to get that ratio. and then I'm just sliding the ruler down to see my process. So in this case, here's my process line in blue. If I had a 0.8 sensible heat ratio, which means I'm doing 80% sensible, 20% latent, I'm not doing a good job dehumidifying, I would have this red slope, and then my process, my actual process line would match that slope. So I slide my ruler down, that's this red line here, and you can see I'm going to have a resultant higher conditions off of the coil over here. All right, quiz question number 7. Let's pull that bad boy up. Which factors affect dehumidification performance? Your choices are A, fins per inch, B, air velocity, C, coil depth, D, all of the above. I'm going to pull up the questions you guys have for me and see if anything needs to be addressed. All right, so far everybody has the correct answer. You guys are doing fantastic. Damn it! One of you guys clicked on the wrong answer. I'm so mad at you. I'm going to go look at that report and see who did it. I almost had a perfect question. You probably just did it when you heard me say that just to mess with me. 99% of you have the correct answer. 82% of you have already answered. So I'm going to close this thing in 5 seconds. 5, 4, 3, 2. And it is closed, and 99% of you got the correct answer, which is D, all of the above. The fins per inch matters because that gives me more surface area. The air velocity matters because the air goes through the coil more slowly and hence touches the surface area. And the coil depth matters because that also gives me more surface area. So D, all of the above. Put that back down. Oh, we did have a question pop up. Is the sensible heat ratio only affected by bypass factor, or are there other factors on the type of load that affect this as well? I'm not quite sure I understand what the other factors would be. Give me an example of what another factor would be. I want to say no to your question, Michael, but before I say no, let me know what other factors you had in mind, and then I'll be able to answer it better. But the bypass factor is the major decision maker here, and there are numerous things that contribute to the overall bypass factor, but that's the major decision here. Okay, so here's one I can tell you. So the sensible heat ratio is affected by the bypass factor, and that does affect the sensible and latent loads, but also the temperature of the refrigerant or the chilled water would have an effect on that as well. So if we just slid back, just to answer Michael's question slightly better, if we slid back a few slides here, right? So here the temperature of the refrigerant, 50, 45, 40, has effect on this as well. So if I was to draw a line from point D to point B on here, or from D, let's use a 4-row coil for example purposes with 50-degree refrigerant. My line would go from D to the red 4, and I could figure out my sensible heat ratio based on that slope. If I had a colder refrigerant, pink, 40 degrees, I would go from D to pink 4, way down here, and you can see my slope would be much steeper, so my sensible heat ratio would be a much lower ratio, which means less sensible, more latent. So the temperature of the fluid, refrigerant or chilled water in our example, as well as the bypass factor, will contribute to the sensible heat ratio. So hopefully that answers Michael's question. Michael's also asking if there's a high density load in the space, will that can contribute to the sensible heat ratio? It'll not affect the sensible heat ratio, but it will affect where my starting point is, D in this case. So my D on here would be in a different spot. It wouldn't be here. It would be somewhere else depending on the load of my space. So in this case, my space is A. So if I made the space colder, instead of 75 degrees, it was 70 in my space, I would be over here, which means my mixed temperature between A and C would still be D, but instead of D being there, D would be over here. which means all of this stuff would shift down. So my space won't have a noticeable effect on the sensible heat ratio, but it will have a noticeable effect on the outcome of the temperatures of everything involved. Lawrence asks if we can confirm that the sensible heat ratio you're using is at space level and not at the system level. The discussion that I was using here was on the cooling process of the evaporator coil, so that would be at the system level in this particular example that I had. Mike is asking if the choice of the refrigerant would have any effect. At the moment, with the screen I have up, the type of refrigerant is irrelevant. But if I was to pick a refrigerant that struggled to get me those temperatures, 50, 45, or 40, then it would have an effect. The evaporator coil, condenser coil, and compression system would be designed around a specific refrigerant to get to a specific temperature. So whether I had a system that was R22 or 410A or 454B, if it was designed to give me 45-degree refrigerant temperature in blue, at that point, the air would not care. The air doesn't care what refrigerant got me to the 55-degree refrigerant temp. It just knows it has the 45-degree temp. But the choice of refrigerant might make it harder to get to the 45. So hopefully that answers that. All right, let's keep trucking along over here. Go back to where I was. Okay, that's where I was, question 7. All right, so we'll look at evaporative cooling process here. We talked about evaporative cooling from the perspective of that evaporative cooler that we had, the swamp cooler. But now let's look at it from the perspective of a cooling tower. What happens in a cooling tower when we evaporatively cool that system? So in that case, in a cooling tower, and we'll slide ahead for 1 second here. In a cooling tower, I'm evaporatively cooling the air, although I don't care about the air. I really care about cooling the water. That's my goal, right? So my building is going to send me warm water. I'm going to evaporatively cool the air by using the heat of the water, which is going to cool the water. So we're going to look at the cooling tower from the air side perspective, because this is psychrometrics, which is the study of the properties of air. So we're going to look at the cooling tower from the air side of the equation, but the purpose of it is to actually cool the water. So when I'm doing that evaporative cooling, I am going to be following the wet bulb line. And wet bulb lines, if you recall, are on these 45-degree angles here. So right now I'm on the 65 or 66-degree wet bulb line. So if I'm starting over here at 100 degrees and 60, let's just say 65 to make it easy, and 65 wet bulb, if I evaporatively cool the air, I am adding moisture to the air because I'm literally adding water to it. So it means I'm going upward. And I'm cooling it, so I'm going from right to left, so I'm going that way, and then the combination of those two is this direction here. So evaporative cooling, like we talked about last week, moves to the left, and it moves up. I'm adding moisture, and I'm removing heat, moving sensible heat. So on a cooling tower, let's look at this example. We got a few different slides here. This first one is a cooling tower when there's no load on it. Basically, I don't need any cooling right now. So I'm sending 85-degree water out to the tower. I'm bringing 85-degree back. I'm not using anything. All my air handler chill water valves are closed, right? This is you wouldn't normally be operating anything in this scenario, but let's just say all the air handlers closed off. They don't need anything. They're good. I have a 100-degree day outside, which makes it weird that the air handlers would be off, but nonetheless, I have a 100-degree day outside with 65 wet bulb. That's my entering conditions into the cooling tower. If you recall, the wet bulb is always going to be the same, so it's going to stay 65, but I'm going to cool it off 100 down to 70 something in this case. So I got 100-degree air coming in. I'm going to take the water from the building and mist it through the air, just like I did with that swamp cooler. Mist it through the air. My fan is going to draw the air through that moisture area, and that's going to cool the air off, and it's going to leave, in this example, 70 degrees, and it's still going to be 65 wet bulb because that's what I had started with. My temperature is going to change. My dew point is going to change. My grains of moisture is going to change, but my wet bulb is going to in fact stay the same because I am following the wet bulb line process here. That's the guy that's going to stay constant in this scenario. Let's look at it when I have it under full load. So on full load, many cooling towers are designed to provide 85-degree water to the air handlers and return 85-degree water, 85-degree water to the chillers. Sending it to the air handler wouldn't help me very much. 85-degree water to the chiller. The chiller is going to cool that refrigerant down with that 85-degree water and send me 95-degree water back. And then I'm going to use moisture to cool the 95 down again. So same day, 100 degrees outside, 65 wet bulb, but now I have 95-degree water entering here, which means I'm not going to cool it from 100 down to 70. I'm only going to cool it from 100 down to 89 in this scenario. So I'm going to have a difference there in the water. And then my wet bulb, in this case, is actually going to change. It's going to go from 65 up to 85 because I am, in fact, adding latent heat by adding the warmer water here. So that's a pretty extreme example in this case. From the air side, it's pretty extreme. Someone had previously mentioned, would it make a difference if I used cooler water or warmer water for the Adiabatic swamp cooler? And I said, nah, it doesn't make a very big difference. It's kind of negligible, right? Because in that scenario, I'm thinking, well, do you have 55 degrees city water or do you got 65 degrees city water? So it might make a difference there. But in this scenario with 100 degrees up here, it is kind of a noticeable difference. So I guess maybe I would change my vote a little bit on that Adiabatic cooler. But it's going to cool that down to 89 degrees. In that process, my water is going to be cooled because I'm taking the latent energy, the latent heat out of that 95 and sending it out. And I am thereby cooling the water down to 85 to send it back. So if we look at that on the psychrometric chart, if I start down here with my 100 degree entering air on the cooling tower with 65 wet bulb, so that's that dot right there. The actual grains of moisture is 36 grains of moisture. I've added from 36 up to 178 grains of moisture. So this water spraying into the airstream is adding those grains of moisture going out there. So I've added a bunch of them there. So that's why the moisture and content is in fact going up. I'm also getting that evaporative cooling effect. That's why I'm going from right to left. So I have kind of a curved line going up. I added a lot of moisture in this case to get a very small amount of cooling. Getting 10 degrees of cooling by adding a ton of moisture to that. That moisture is coming obviously from the building condenser water, and a lot of that moisture is leaving, which is why I'm also going to need makeup water on the cooling tower system. Because as that moisture leaves, that means I have less water in the sump than I had coming out of the nozzles, so I constantly have to keep adding water to the system, makeup water to the system. All right, let's look at another process, heating and humidification. This is what I would typically do at a residential home when you have a humidifier. You would wait for a heat call in order to run the humidifier because it is in fact easier to get warmer air to absorb that moisture because it is drier, lower percent relative humidity. You might also do this in a commercial building, but usually heating and humidifying is pretty common residentially. So in this case, I have 70 degree air with 54 degree wet bulb, 40 degree dew point, and I'm going to add both temperature and moisture to the air. So I'm heating it, let's say with a furnace, and I'm adding humidity with a humidifier, running moisture across the evaporative pad and blowing it in, or a steam humidifier or something like that. I can look at the amount of energy by either. So first off, I should say I'm starting at point A, ending at point B. I'm heating it, in this case, 30 degrees from 70 to 100, and I'm adding 15 grains of moisture by going from down here up to there. So my total process is A to B, so it's to the right and it's up by heating and humidifying simultaneously. Mathematically, I can look at what's going on there for the energy of the sensible, the heat of the sensible, 1.1 times 1,000 CFM times a 30 degree delta T, 33,000 BTUs. The latent formula, if you recall, is 0.69 times the CFM times the delta grains, in this case 15. That gives me 10,000 BTUs. My total energy is 43,000 BTUs. Heating and dehumidification. I could probably almost skip this slide because I don't know when you would even do this. Like, this is not normally a thing you would want in most applications, but I'm heating it. I'm going from point A to point B, 85 to 100 degrees, and then I'm dehumidifying it also. You wouldn't normally do that, like I said, but if you did in fact do that, you'd be moving to the right and down. and then there's the formulas for that. Same exact thing as heating and humidifying, except instead of going up, I'm going down. So then this number becomes a positive number instead of a negative. Well, if we didn't even show it, it would have been a positive, and we would have had a negative, but we didn't even show it as a negative here. All right, so flashing back to those process lines that we had. Once again, sensible cooling. If you could even do sensible cooling without dehumidifying, I guess you can. And if you want to know how to accidentally do sensible cooling, join us for the webinar this afternoon at 2 o'clock. We'll accidentally sensible cool. But you were going straight to the left. Sensible heating would be straight to the right. Humidification is straight up. Dehumidification is straight down, right? Because I'm adding moisture, grains of moisture, or removing grains of moisture. If I'm doing some combination, which is the more normal scenario, cooling and dehumidifying, then I move down and to the left. Evaporative cooling is left and up. Heating and humidifying simultaneously, like at your house, is to the right and up. And then you would almost never heat and dehumidify, but it would be down and to the right. All right, getting towards our last section here. As you guys have more questions, please do type them in the question chat box, and I'll do my best to try to answer any of those questions. But let's look at plotting out the whole system for a particular, say, room or house or whatever you want to think of it as. Let's just pretend it's an office at somebody's building. So up here on the left, we have a pictorial drawing of our air handling system. Where you start on the air handling system is kind of irrelevant. Most discussions usually start with the room. Most air handling manufacturers start with the return air as their thought process, but we're going to start with the room in this case because that's what I really want to solve. My room is too hot, my room is too cold. So I got the room. He's point number 1. Point 2 is the return air. It moves through the air handler. Some of it might be direct exhausted out, like maybe you got a bath fan or something like that, exhausting some air out. Some of that return air comes through and mixes with the outside air. Some of that might be additionally exhausted out. So maybe you have 100 CF from a bath fan exhausting here. Then the rest of the return air travels through, and based on how much outside air you're sucking in at that moment, you may also need to exhaust some air out to relieve that pressure and keep things balanced. But the return air would come and it would mix with the outside air. That's point 3. We would call that our mixed air condition. That goes into my either heating or cooling coil, usually not both, but sometimes you might run both simultaneously, but usually not both. We'll use the cooling coil for right now. So the mixed air number 3 is my entering condition to my cooling coil. Then number 4 is my leaving condition off the cooling coil. Number 5 is my supply air out of my fan system, going down to my diffusers over there. So if we were to look at that plotted out on the psychrometric chart, point number 1, my space condition. Point number 2 is going to be slightly different than my space condition, right? Because let's say my room is 75 degrees, but maybe my return air is 78 or 80 degrees or something like that. So in this example, they are showing 75 room air, and let's call it, I don't know, 77 return air. Because the heat of the room is going to rise, the return in this case is up towards the ceiling, so it's going to be slightly warmer than the space condition, right? Then also, depending on where my ducting system is, it might even increase from there. That 77 may become 79 or 80 because A, the friction of the duct, and B, if this is going through a warm space, a warm ceiling cavity, an attic, something like that, it will have an effect on here. But for this purpose, we don't really know what that is because we don't know where the duct's located. We don't know if it's insulated very well or at all. So for right now, point 2 is going to make his way all the way through, scot-free, if you will, to the mixed air scenario. Then he's going to mix with the outside air. So here's point 2, return air. My outside air is way over here. What I would then do is a mixed air calculation like I showed you before. There's also calculators online you can do that with. You need to know the CFM of the outside air, the CFM of the return air like we had mentioned. If I know those two things, I can figure out if I'm going to be X% close to the return air line. So in this case, we have, I think it was 33% outside air. So that means I'm going to be 33% away from the return air dot, 67% away from the outside air dot, and that gets me to point 3. Then I'm going to run that through the cooling coil, where it's going to be cooled, moving to the left. Once it hits the saturation line, or some of the air hits the saturation line, it will then be cooling and dehumidified following the saturation line down here. Number 4, number 4 is not right on the saturation line because we did have some bypass, so he's a little bit offset because of the bypass air. So really there's like point number 4 on here and point number 4.1 on here, which is the cooled air and the bypassed air mixing together. Then I'm going to pick up a degree or 2 of waste heat off of the fan motor, and that gets me to number 5, discharge air. And then that discharge air is going to make its way into the space. You can see it is also slightly warming up depending on where that duct is actually running through. And then once it enters the space, it's going to warm up the rest of the way, because it might be 55. Let's say I made 55 off the coil. Let's say it leaves the fan at 57. Let's say it gets to the space at 58. And then the 58 and the 75 degree room air are going to mix together. So that's 0.5 to 0.7. Those two things mix together, and they keep mixing until it gets to the 75, because it in fact is 75 in the room. And then the process would repeat itself. All right, so that's just kind of showing you what I just said, but I kept the other screen up because it had the psych chart on there as well. If you want to look at that particular example that we just did on the psych chart, right, it's just a randomly chosen example, but it would show you on here on the slides all those conditions that we had and why we had the scenarios that we had. If you know any 2 points, obviously the title and the airflow are independent, but if you know any of these 2 points, dry bulb, wet bulb, humidity, relative humidity, real humidity, enthalpy, and dew point, if you know any 2, you can plot it on the psych chart as we discussed last week. So in this case, my room air was 75, my out air was 90, right? That resulted in my mixed air being 81, but I also had to do the mixed air on the wet bulb side, so 72 and 62. My mixed air became 66 on the wet bulb, right? My mixed air, number 3, goes through the cooling coil, so mixed air, 81, 66 in this case, goes through the coil where it is 57, 56 wet bulb. Then it goes through the fan where it picks up a little bit of waste heat. That's pretty much sensible waste heat. So I pick up a degree in this case there. And then my supply air goes into my room, 0.5 to 0.1. And I'm repeating the process over. So those 5 processes are the room process, cooling the room down, the return air being sucked back in the return duct and possibly being warmed up by the conditions of the return duct, the outside and return air mixing process, the air going through the cooling coil, including its bypass discussion, that process, and the supply process, which is the fan waste heat plus any duct gains. Those are my processes that I have. Let me see if we have any questions. I think I saw something pop up. Oh, excellent point, Doug. I think he was talking about when I was way back here, and I said, I don't know why you would ever be doing heating and dehumidification. And I need to think about it more the way Doug was thinking about it. Relabel this, instead of heating and dehumidification, how about dehumidification and reheating? So sometimes you'll dehumidify well below the dew point that you otherwise wanted to pull a lot of moisture out of there, and then you have to reheat it to temper it back up. So excellent point, Doug. If my brain just stops thinking of it as heating and dehumidification on the slide, and we think about it dehumidify and then reheat to temper it back up, that is when we would in fact use this process line. Excellent, Doug. Love it. In the system, Philip asks, in the plot system, do you consider filter pressure drop significant? Only one filter needed, or multiple, or in multiple location? The filter itself is going to have no effect on this process here, because the filter is going to clean the air, which is fantastic. No effect on this discussion. And it's going to have a pressure drop associated with it, which is already factored into the CFMs that I'm dealing with. And in this particular case, this fan is running whatever CFM it has to run at to overcome all of the static resistance of the entire system. All the resistance would equate to return grill, return duct, coil or filter would be right here, filter, heating coil, cooling coil, supply duct, and supply grill. It's already factored into that discussion. So the filter has no effect on this particular system process. Now, with that being said, if you designed the system for certain CFMs and based it on certain static pressures of all the static pressures I just mentioned, and then your filter gets dirty, or you take your filter out and you put in a filter that has a different pressure drop than was expected when we designed the system, that additional filter pressure drop is going to cause my supply fan to ramp up if I have a variable spot fan. If I don't, it's going to cause me to have a lower CFM, which then is going to affect the whole process. So if I have the filter in there that the system was designed around, then the filter pressure drop is not part of the discussion of the process. But if I swap the filter out and put in one with a higher pressure drop, it may in fact have an effect on the overall process, or will have an effect on the overall process. Let's see. Daniel says, I gotta spread this question out so I can see it more. Holy cow, Daniel, it's too big, I can't see it on my screen. Make Dan's question box bigger. All right, Daniel says, lots of process dehumidifiers add a lot of regenerative heat to the airstream as well. Most dehumidifiers actually also heat the air a significant amount. Yes, correct. He's on the same thought process as Doug was with the dehumidification plus reheat type of discussion. All right, going back to our system plot here, we just talked about those. All right, so where does this psychrometric discussion fit in the overall design process? It's typically the second thing that we're going to do in the design of the system. The load estimate is where everything begins. So first we do the load calc, then we're going to do the psychrometric analysis to figure out the conditions of the coil that we need in order to achieve the loads that we estimated. Then based on the psychrometrics of the conditions we need of the coil, we will then pick a coil. Once we pick a coil, because of the dimensions of the coil, that'll pick the size of the air handler that I need. My refrigeration plant, my cooling plant, will be based on the summation of what all my coils need. My duct system will be designed based off of that load estimate and CFM that I had figured out from the psychrometric calculation. And so that determines what I need to put into each room. I'll do a load calc for each room. My duct design is based off the load calcs of the room, smaller ducts to rooms that need less cooling, bigger ducts to the other rooms, obviously. Then once my duct is designed, then I can pick my fan system. Then I can decide how I'm going to control the whole dang thing. So this is just one of many pieces of the design process. For you guys that have been to our TDP class, Technical Development Program, you know that the psychrometric discussion we're having today is part of that overall program. We do that every fall. I'm trying to think. I think is it 11 weeks we do it now? We meet typically every Tuesday for 4 hours for like 11 weeks. Psychrometrics is in fact the second thing we do in the class. We do ABCs of comfort, then we do psychrometrics, then we do load estimating. I know that that's not the process I'm showing on the screen here, but that's the order we do the class in, and there are reasons we do that. But the system design is a little bit different than the class. And that class covers all kinds of stuff. It covers the things on the screen here, fans, coils, it dives into chillers, acoustics, indoor air quality, all that good stuff. So watch for that next fall, assuming that we don't have a quarantine next fall, God forbid. And we'll have that technical development program like we have had for the past 40 years start up again in September. All right, quiz question number 8. Where's my poll questions? Okay, number 8. This one's super easy. Hopefully nobody gets it wrong. How would you rate this course last week and this week, the psychrometric course that we're doing? For purposes of your PDHs, your answer does not matter. There's no right or wrong answer, although I think number 5 is in fact the correct answer. But there's no right or wrong answer. This is just, once again, we got to prove to give PDHs that people are actually attending and they didn't just open their computer and then go to lunch. Not that you could leave right now and go somewhere for lunch, but if you could, where would you go, right? So we'll leave this open for another minute here. All right, 84% of you answered, so I'm going to go ahead and close this down. 5, 4, 3, 2, 1. And I would share the results on the screen with you, but I did so bad, I don't want you guys to see how bad I did. 5% of you did not think this was a great class, and I'm very sad about that. Actually, no, it's fine. 95% is great. Can't make everybody happy. The ones that didn't think it was a great class, feel free to send me an email later on letting me know what I'm missing, so the next time I do it, I can add the things you think were needed to make it even better. I do really appreciate the feedback. Let me answer this other question while we can, because somebody had asked, you mentioned we can see past webinars. This is Philip asking that. Please share the link where that is located. I will send you guys the direct link, and I'll put it in the little chat box over here for those that want to click on it. But if you wanted to find it, It's tecmungo.com. That's our website with all of our normal stuff on there. If you click on the training tab, I think I got my screen showing. I do. And you scroll down here, there's 3 kinds of training. There's classroom training, which you can check out. It's not super exciting right now because everything's been postponed for a few weeks. But all that classroom training is on there, and you can see all the classes we have coming up, whether it's a rooftop service class or whether it's a residential controls class or whatever it is. All that stuff is on there. You can click on any one of those things and register for them. The third tab is our YouTube channel. If you click on that, you would be brought over to our YouTube channel where we have like 160 some videos on there, all kinds of different topics. There's just tons of stuff on there. There's also playlists on there where you can go look at categories of topics. So if you want to learn about, I don't know, installing Ecobee stats, servicing vane axial rooftops, how to price a residential job correctly, how to use your electrical meter, all that kind of stuff is on there. All those little like 8, 10, 12-minute type topics. And then the very last tab, or rather the middle tab, if I go back, is the online stuff that we've done traditionally. We've been doing these since 2010, so there's a lot of stuff on here. You'll find both the live, i.e. this class we're doing right now, and the recorded sessions on there. So today, this afternoon, we have a class, Supersize Me. Psychometrics we're doing right now. Wednesday, we have a load calc class. If I look at the recorded ones, they're kind of in reverse date order. So these are all the ones we did last week. And you can click on any one of these. Let's just say you wanted to learn about the ComEd $700 per ton rebates. You would click on that, and it would start playing that particular one. In some cases, depending on where it's posted and where we got the data set up, it may ask you to log in first. Let's say you wanted to do so you wanted to learn about rooftops and that humidifier coil that I mentioned a little while ago. If you clicked on that, it's going to take you to the original registration link. But once you fill that stuff out and put in where you live and all that good stuff, or wherever your office is, whatever you want to put in, where's my office? And click on that. It'll then let you watch the live webinar as well. So that's how those would in fact work. And you can keep scrolling down, and there's just literally over 1,000 hours of training on here. So if you're bored, and many of you are lately, there's tons of stuff going all the way back to like 2010 on here. All right, so in regards to the link, I'll paste that in the chat box here for people that want to click on that because that was requested. Zach asked, do we have a cheat sheet with all the formulas for the physical and thermodynamic properties discussed in the psychrometric chart? I don't have a cheat sheet, but I am going to be emailing all of you this manual that I had mentioned. It's a workbook that would normally go along with this class. It's obviously difficult to do that with the webinar version, but it is 76 glorious pages of things, and it does have the formulas that we discussed in there. It's basically all the slides that we used today, along with some more description of those slides, and then some work session examples that you can work through to test your psychometric skills. All right, any other questions anybody wants to type in? See if I have any other psychometric cheat sheet stuff in my notes. Let's just see real quick. Problem sound session answers book. Nope, I do not have anything that we didn't already talk about. All right, well, with that, I'm going to end the webinar unless anybody else types any questions. I'll stay on another minute or two just to see if another question pops in. But I'll end the webinar. For you guys that needed the PDH hours, assuming that you attended last week and this week, and you answered 5 of these 8 questions correctly, and 2 of them were total give-me's, so that shouldn't be too hard, then you will receive a PDH certificate via email. So if you attended both sessions, you answered 5 correctly of the 8 questions, and you checked the box at registration saying you were a PE and needed a PE PDH certificate, you will get one emailed to you. With that being said, it might take a week because there are several hundred people on this webinar, and we type those up manually. Normally not a big deal, but now there's so many people, it might take a little bit of time. So give us like a week. I'll get everything graded, all the quizzes graded, and Kelly will email out to you guys the certificates. If for some reason you don't see one by next Monday, that means either you didn't pass or we screwed up and sent it to the wrong email or something. So I will email you guys that workbook today, or I'll probably post it somewhere and email you a link to it because it's kind of big. All right. With that, I'm going to go ahead and end the webinar and end the recording, and I thank you guys for your time.